column. Okay, so this is just be one element of big N squared elements in your matrix. Yeah, you define it, hence 3 bars, right? You define it this way. You take, you integrate the phi m, like the mth one of these, times your operator, now a hat. Now, if this matrix is to be a Hermitian matrix, this operator here has to be a Hermitian operator. Okay, so this is a Hermitian operator times phi n. Let's just, well, doesn't matter, but in general m and n will be different, although you can have diagonal mm. Okay, now this we can just rewrite in the Dirac bracket notation, right? Just as phi n, that's the bra, and the ket is a hat phi n. Okay, so the elements of your Hermitian matrix are defined in these terms, or these terms. I mean, these two are just equivalent. They're two different notations. This is the integral, overlap integral notation, and this is Dirac's bracket notation. Okay. Now, because this a hat here is a Hermitian operator, we can learn a few things. We can find some relationships relating these elements of a matrix. Now, a hat is Hermitian, right? So I can move this a hat to the left side. I can move it to the bra, like here, yeah? Because it's Hermitian. Right? We can do that. Did that earlier session. Now, can you remember a couple of sessions back? We showed that if you conjugate a star, if you conjugate the bracket of x, y, look, I'll write it. So if you conjugate the bracket of x, y, you will get yx. Okay. Remember that from a couple of sessions back? So the conjugate of bracket xy is equal to the bracket of yx. Okay? So we're going to use that. Now I can rewrite this. I can reverse it, and I've reversed it, and then start it or conjugated it. So if I reverse and star, I just get back to what I started with, right? Because of this. Okay, but what is this? Well, by definition, it's the definition of an element of a Hermitian matrix. This is just this. That is A of nm. Right? So if you just swap the m's and the n's around, you get this. If you swap the m's and n's around, you get this. Okay, but conjugated, start. So it's just A and M start. Right? Follow that reasoning. So summarizing a little bit. So in other words, you now have a relationship between the elements of a Hermitian matrix, right? And they are, well, the relationship is AMN is equal to ANM start. All right. Now in words, what are you doing here? When you take a matrix and you Mn becomes Nm, so in other words, the rows become the columns and the columns become the rows. Are you familiar with the verb that labels that phenomenon? It's called transposing. So in effect, let's see. I'll try. Yeah, I'll do it with my left hand. So when you transpose a matrix, you're making the columns become the rows and the rows become the columns. So if these are the rows of your matrix, when you transpose that matrix, what you're doing is doing that, right? You're doing that. The rows become columns, and the columns become rows. You're transposing the matrix. So, if now we can actually define a Hermitian matrix directly without having to worry about this. I can just say, if you have a matrix where if you transpose it and conjugate it, then what you get is equal to what you started with. If that happens, if this equals that, then by definition that matrix is Hermitian. Okay? So if that equals that, you have a Hermitian matrix. So if the elements, so if your in words, if your matrix, when transposed and conjugated, if it equals the original, that matrix is Hermitian. Okay. Now, why are we talking about this? Because it's a kind of lead-in. It's a stepping stone for the next chapter. In fact, when we come to deal with angular momentum and spin, it's actually more convenient to work with Hermitian matrices than with Hermitian operators. Now they're equivalent, right? I mean, there's an equivalence between the matrix and the operator. Right? You can easily define one in terms of the other, but it's just in practice. You'll see when we get into next chapter, chapter 7, when we're dealing with when your observables are angular momentum and spin, which are the two are related. Okay, so this is a kind of stepping stone. It's a tool. Perhaps I shouldn't have put this line in here. You know this is true. It's just the definition of a Hermitian operator. So you can bring this A, from the ket side, the right hand side. You can bring it over to the left side here, and because it's Hermitian by definition, this equals that. So there's a kind of almost like a symmetry. It doesn't really matter where the A is. Do you put it on the right hand side? With
vast virus database has been updated.
With the ket, or do you put it on the left hand side with the bra? It doesn't matter, right? If A is Hermitian, it doesn't matter if it's on the right hand side or the left hand side. So this line here is leading up to another notation where instead of writing the bracket with an operator, Hermitian operator, A hat, in this form or this form, there's an alternative, and that is you just put a second vertical line here around the A. So you'll have phi m, first vertical line, A hat, second vertical line, phi n. Okay, so our bracket sort of disappears, and now we have this sort of bra A hat ket, right, with two vertical lines. So that's what this leads into. But ran out of boards.